This is the first in a series of short videos on the Hoekstra performance curve model for gasoline desulfurization. The key to optimizing a gasoline desulfurizer is to maximize desulfurization and minimize octane loss. That's why we focus on a single curve of octane loss versus product sulfur, and we call it the performance curve. This is the performance curve, delta Ron octane versus product sulfur, for a feed we have analyzed. This is a full range feed. Now we change the feed, everything else is the same, and we see the curve shifts up quite a lot, just due to the differences in the feed composition. Now we add a splitter that removes the C5- light naphtha, and we calculate the dashed curve, which is higher because the C5 olefins are now bypassing the hydrotreater and are not being saturated. That octane savings is calculated and reflected in the curve. And we return to feed 1 and see the effect of a splitter for this feed. Now I'm going to remove the splitter, and I'm going to say, what if I could double the selectivity of the process, the octane sulfur selectivity, and that's what this purple curve shows. Now, doubling the selectivity of the process is a bit difficult, but in this spreadsheet I can set the selectivity to whatever value I want. So I'm going to set it here, reduce it from 200 to 140%, which is more realistic and can be achieved with a new process that's available today. A selectivity improvement represents a fundamental improvement in the selectivity that's caused by a change in catalyst or reaction conditions. And then I can also add a splitter and see the combined effect of a 40% selectivity process improvement and a splitter. That's the dashed purple curve. Here's how this performance curve model works. The 759 compound analysis is a detailed hydrocarbon analysis that quantifies the concentration of every compound in the feed. The analysis is reduced to a 10-lump feed vector that measures the concentrations of 10 groups of compounds corresponding to 10 key reaction paths. These 10 numbers are then fed into a model that has two parts. The selectivity model calculates the changing gasoline composition that occurs along each of the 10 reaction paths, and the octane model calculates octane as a function of composition. Both these models are, we believe, the best available models for this purpose. The output is delta octane versus product sulfur, the performance curve for that feed. In this model, two other factors can affect the performance curve. We start here with the standard performance curve for full range feed 1, and I will include also the curve for the new process with 40% improved selectivity. Now this first factor I will change represents additional octane loss that occurs at especially high reactor temperature. Some additional reactions add to octane loss near the end of the cycle and move the curve down, as I have shown here. And secondly, reducing the endpoint of the gasoline will tend to move the curve upward, and I am showing that effect here. This tool is being used today for decision making on capital investments for Tier 3 gasoline, licensors, process design, feeds, cut points, catalysts, and Tier 3 strategy. If you have a gasoline desulfurizer, your engineers and planners should certainly have this tool. With analysis of your feeds and this spreadsheet, you will be able to see exactly what is happening in your unit to change octane and sulfur, make accurate performance estimates, and make better decisions for Tier 3 gasoline. In a subsequent video, I will give more details on how the performance curve spreadsheet works. Thanks a lot for your attention. The performance curve model uses the results of a 3-year multi-client research project, and it has been validated in field testing on many commercial units. The reports on our research project, which include this model, are available immediately to anyone at negligible cost. Please contact me anytime for an offer letter. Thanks and have a good day.